Hello there, welcome back to our channel. And today I am going to talk with you about uh, simulating an IV characteristics of a transistor, especially the bipolar junction transistor. So you can see that I have this NPN transistor right here that I have chosen. So why we need to do this? So remember, the IV characteristics is the curve between an output current versus output voltage for a given values of input. So in case of a common emitter configuration, as you can see, I have this NPN transistor. I know it is NPN transistor because of this direction of the current that arrow shows. And here is the three terminals. That is the collector, this is the base, and that's the emitter. Now, it's a common emitter configuration. As you can say, this is an input part of the circuit, that's an output part of the circuit. This is the base emitter side, and this is the collector emitter side. Well, the emitter is common to the base and to the collector. That's why we call it common emitter. In which case, my output current is the collector current, and the output voltage is the collector to emitter voltage. And the input for this transistor is the base current that I am going to inject into the base of this transistor. So when you do a discrete electronics design using BJTs, FETs, a MOSFET, etc. So when you use a transistor, you basically need to know the Q point, or also called as bias point, or also called as operating point. You need to know this to set up a DC biasing. Here in this circuit, DC biasing is not shown, and this DC biasing is set with the circuits using transistor to provide the DC voltage to make the base emitter junction and the collector emitter junction to work in the active region, forward region, etc. So we have seen that before. So basically your operating point helps you to set the transistor operate in a region of operation, desired region of operation. So we know that there are many regions of operation. One is called as active region, one is called as cutoff region, one is called as saturation region. And all these regions are applicable depending on whether you operate your transistor. We are talking about BJT in common base, common emitter, or common collector. So coming back to this curve, you have IC and VC. The input current is your IB. So when you increase uh, the base current initially, so with the increment of VCE, your collector current also increases, but after some point it saturates, your current is saturated. So this is for, let's say, the value of current IB1. Then you have like another, you increase the current more, so you have increment of your IC. Your IC is also increasing, IB2. Then you again increase your base current, and your collector current is also increasing. And then you again increase your base current, and your collector current is, this is IB3, this is IB4, is increasing. And nearly we see that if you increase the VCE more than required, your currents that is the collector current, is saturating after a certain value of your VCE. So essentially, you can actually relate this with this green curve, and you say that the area of operation, this part of the green curve is called as linear region of operation. This part of the curve, you call it as a saturation region of operation. Rather, I would say saturation. Okay. Now you have this understanding that you have a linear region and then you have a saturation region. So there is a linear relationship. You increase the IB and you increase the IC. You increase for a constant VC. VC is almost constant. But after certain value of VCE, if you increase the VC, your current IC is saturated. And that's it about. So relationship between IC and IB is straightforward, is called as IC is equal to beta times IB. It can also be written as HFE times IB, where beta or HFE is called as DC current gain. Okay. And for a given transistor, when you design circuit, discrete design, you in a manufacturer datasheet, you will find the value of beta. In a moment, I'm going to show you that. So that beta value is your gain. So if your beta, if for example, is about 200, which is the case for this transistor part, that is 2N2222 from the manufacturer. I will show you in the SPICE model, the value of beta is 200. And then you need to actually know for a given value of VCE, for a given value of beta, actually, you can derive the curve between IC and VCE for the given values of IBs. And from that, you know the Q point or the bias point or the operating point. For example, if I start from 0 here, and then these voltages are like 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, and so on. And then these values are like 1, 2, 3, 4, 5, and so on. And this is, let's say, a milliampere range, and VCE is expressed in volts. So now, if that is the situation after plotting this curve, after knowing the regions of operation, I would say I want a VCE is about 5 volt. That is the voltage drop across the collector and the emitter. This is VCE. You see, this is the collector and this is the emitter. So VCE, I want it to be 5 volts. And then I can actually see that for value of IC, if I am requiring the collector current, which is essentially a load current most of the times that will flow through the load, is required to be 3 milliampere. So then I would just draw these curve, these lines to determine, and this will be my Q point or bias point of the transistor. So for a required value of IC equal to 3 milliamp and VC is equal to 5 volts, I know that my Q point or the bias point is IC equal to 3 milliampere and VCE is equal to 5 volt. Now, since the IC is equal to 3 milliampere, I can estimate the value of the base current. In that case, the base current IB would be IC divided by the beta. Now I know this is 3 milliampere from the specification and the beta is 200. So accordingly, I'll get the value of IB. Okay, so I explain you what is the IV characteristics of the BJT is, what's the concept of current versus voltage, what is Q point, why it is important. So basically, when you have this Q point, that helps you to set the DC biasing of the transistor. And then after this setting this Q point, around this Q point, your small signals or the inputs and outputs can be varied. It means when you apply a small AC signal at the input, and then you have a large AC signal amplification, due to amplification, you have a large output. So that those signals, whether current or voltage, will be varying across this Q point. Okay. So now what I want to show you is, let me just clean this drawing bit here. So here I have chosen a transistor called as 2N2222. That's my transistor. Okay. And then at the base, I am applying this current source to inject a current IB. And as you can see, emitter is grounded. And then at the collector, I am applying the voltage of, let's say, 30 volt DC, and it has a value of 10 microampere, the base current. So if I apply a 10 microampere, the beta of this transistor, let me show you that. So I will right click on this transistor part, and then I see here the transistor is, the properties are shown, the manufacturer is shown, polarity is shown, VCO, open circuit voltage across collector and emitter is 30 volt. Maximum collector current it can handle is 800 milliamps. Now I will click here, and here this first highlighted line shows me the spice model of this transistor. And then I see that here the beta factor is given to be 200. So I have this 200. So I will just click OK. And now I have applied about 10 microampere, the base current. The beta would be 2000. With the beta equal to 200, I allow collector current to be 2000 microampere. So it's about 2 milliampere with the VC equal to 30 volt. So let us try to see the bias points or the DC operating point of this transistor. So what I will do, I will simply name this net also. Let's call it as VB, the voltage at the base. And I will say just this is the net, and this is, I know this is the emitter is grounded. So all voltages will be measured with respect to ground. And this is the net, that is VCE actually. Okay. Now I will run one analysis, simulate, edit simulation command. I want to run the DC operating point. So I will just see that. Before that, I will just disable this analysis that I have done before. So I will explain that in a moment. I will just disable like this, putting this sign, and this is no more active. Then I will click simulate, edit simulation command, go to DC operating point. And now with this, I don't want that. I just want .op syntax, and that's it. This command is ready. Now what I see here is this is the base voltage. So there'll be a drop when I'm injecting the current IB into the base. I am going to have this drop across the transistor, that is VBE. And then there is this drop across the transistor, which is VCE. Okay, so usually for a silicon transistor, this is about approximately 0.65 to 0.7 volts. So we'll see that in a moment after running this analysis. So click run right here. So I will click run, and now here I am with all voltages. So the first voltage at node 00130, which is the voltage across collector to emitter. Then the voltage at the base with respect to ground is 0.67 as predicted. Look here, the voltage here was 0.65 to 0.7. That's correct. Now the collector current is about 2.5 milliamps. So we predicted it's about 2 milliamp, and it is about 2.5 milliamps. So close to what we uh, predicted theoretically. Beta times IB. IB is 10 microamperes, and the collector current, emitter current is, of course, the sum of IB plus IC, right? And that's the current drawn from the VC voltage source, which is 2.5 milliamp. So that is it. That is it. If we don't have VCE, if we set it to 0, then the collector current will also be 0, even if we inject the base current through the transistor. Now, the purpose of this tutorial was to show you and demonstrate you the IV characteristics of the transistor, discrete transistors, that we use in our variety of electronic design, and understand how to choose a bias point, because if you design an amplifier or any other circuits, you often need to use a transistor and use it with a proper DC biasing. With that, for that, you need to set an operating point for a given values of the currents and the voltage, the output current and the voltage across the transistor. Okay. So we see that this region base to emitter is forward bias, because the base is positive with respect to emitter, and then base to collector region is reverse bias, because the collector is at relatively higher positive voltage than the base. Here is 0.7 volt, but here is 30 volt. Okay. And that's it. So you bias the transistor in active region. So let's now run the analysis. So what I'm doing here, I'm going to explain this. I will first enable this command by putting dot there. So this command is, so I'm sweeping the voltage source VCE from the value of 0 to 30 volt at the steps of 1 volt. So here in the curve, I'm sweeping from 0 to 30 volt at the steps of 1 volt. And in the same analysis, I'm sweeping the input current source IB from the value of 0 to 20 microamps at the steps of 1 microamp. So first IB1 value will be 0 right here. Then IB2 will be 1 microamp, then IB3 will be 2 microamp, IB4 will be 5 microamp, and it will go up to 20 microamp. And because of this sweepings of both output voltage and the input current, I will have the plots of the output current IC. Okay, so exactly the same plot I am expecting. And then I will be able to draw the line between linear region and the saturation region. And from that, I will be able to extract the values of Q points, and as well as the value for a given IB, for a specified IB. Okay, and I will also know the value of IB, and I will also verify the theoretical beta with the practical results. So let's do that. So I am going to sweep this, and now I will just clean all the drawing so that you better see the things. Now I have this clean waveform window, and there I want to plot the current through the transistor. So here on the schematic, I take the probe in the collector terminal of the transistor, and if you see on your screen, extreme left bottom, you have this instruction, left click to plot IC of Q1. That is prompting, this spice is prompting me to plot the current through the collector. So I will left click the mouse button. And if I right click the mouse button, it will help me to edit the transistor part. But I want to plot, so I will click the left button. So I do that. And here you are, you see that I have on the x-axis the VCE that's varying from 0 volt to 30 volt, and on the y-axis my current is the collector current from 0 to 5 up to 4 milliampere. And these are different values of IBs for which the IC is being plotted. Now, I want to know the Q point of this. So for example, let's say I'm designing an amplifier where the output voltage of the transistor, which is the VCE, I want to be, let's say the supply voltage, the maximum voltage of the transistor is 30 volt here, and I want to have the voltage for an amplification across the transistor to be 15 volts. So half of the VCC. I want VC to be half of the VCC. So VCC is 30 and VCE I want to be 15. So I have this 15. And then from this 15, I am given the IC to be chosen as 2 milliampere. So right here, 2 milliampere. So I go here, and somewhere here, I will have that Q point, right? So my Q point here will be IC equal to 2 milliampere, and the voltage at the collector of the transistor with respect to emitter, where emitter is ground, is 15 volts. Okay, for the supply voltage of 30 volts. So why 15? Because from this midpoint, I can have the swings, output swing up to 30, and from 15 down to 0. So maximum swing, I expect like 30 volts. Okay, peak to peak. So, but I want to now know what is my base current. If the collector current is 2 milliampere and the collector voltage is 15 volts. So I want to know what is the base current for that. So for that, what I do, I just right click and then I click view. I see, take the mouse on the view, and here I can select the steps. So here it shows me the steps for which the value of IBs are given. So I want to choose the value of IB for which I will be given the value. So if I theoretically want to calculate the beta, actually, for a given value of IC equal to 2 milliampere, so the beta is 200, as we saw before. So IC, remember, IC is now 2 milliampere from the waveform, and beta is 200. So IB would be IC divided by beta. So it is like 2 milliampere divided by 200. So how much it is? Like 2000 divided by 200. So it is about 20 microamp, is it? 1 second, let me check that out. It will be 10 microampere, right? So the value of that. So let us select this value, which is about 10 microampere right here. Okay, because that's the step 11 will give you the value of IC to be 2 milliampere. So let me select that, click here, 11, and select OK. And you see approximately at 15 volts, you have a current of 2.1 or 2 milliampere. So that's how you basically decide the operating point of your transistor. So hope you like this video, and if you did so, do like, comment, and share with others for wider reach, and stay tuned, because with this knowledge we are going to design a common emitter amplifier for audio applications. So we'll need to understand and refer back to this knowledge of DC, the output characteristics of a transistor, operating point, and everything. Okay. Wish you happy learning.